So Jebin, Mohandas is at Intel India Technology Private Limited. The title of his talk is Chiplets Design and Verification and Methodology Perspective. And as a short biography, he has over 20 years experience as a leading expert in RTL verification and verification methodologies, specializing in advanced techniques like OVM, UVM, debug using Verdi. He has significantly contributed to reducing defective parts per million through robust flows in RTL. Jebin's expertise spans static clock domain crossing checks, reset domain crossing, RTL linting, low power checks, alongside RTL constraints verification, power estimation, and formal verification. Currently, he is focused on enabling the left shift in the VLSI design cycle to improve turnaround time and reduce bugs. Jebin is also an active contributor to the Accelera CDC, working on standards for CDC abstracts to enhance vendor interoperability. Okay, over to you. Thank you, Jebin. And you have 15 minutes, please, Jebin. Thank you.
Hi, everyone. So just a background on what is a system of package, and as all of us, we might be aware. So essentially, each of this block here is a chiplet. So until few years back, these used to be the complex chips. So now, as the demands are increasing, so we are forcing multiple complex chip into a single package. So as you see from here, so we have a die or a complete SoC which is on 2 nanometer and another die on 3 nanometer with latest nodes 18A. And we are not only connecting these packages, the dies, but also we need to have extensive debug capabilities. Security is an important factor, and we have analog blocks. So is the memory, the high bandwidth memory requirements are increasing day by day with the improvements or the requirements of the AI workloads. And also we have latest protocols like UCIe, PCIe, CXLM, and all this for the different connectivity between the die-to-die or maybe sometimes between the external SOPs as well, right? So overall, this system is becoming very complex. So what maybe 3 years back, whatever we did, like it has become maybe if there are 5 or 6 SoCs of the yesteryears which are packaged in a single package with complex die-to-die packaging protocols. So that is a scale of the complexity, right? So each of this block can have a few hundreds to 1,000 plus IPs. So now when we say into 5, so typically these that 4 blocks, right? 2 nanometer, 3 nanometer, yes, GPU, NPU, CPU, and compute. So this will have most of the IPs and all the functionalities. So on top of this, the software, so today, it's no more a chip or a system of package. The whole system is considered as an unit, right? So the direction is every product is not delivered as a chip, but it is delivered as a chip with a package, packaged and with the software, right? Software stack completely tuned for this SOP. So with this, we can just imagine the quantum of bugs that can arise, right? So that's where the verification plays a very important role. And with our traditional approaches of verification, it becomes very challenging. So that's why we need AI ML techniques and all out of the box way of verifying this, right? Because traditional verification cannot scale. And any issues we see here at the package level, debugging them is a challenge, and going back and fixing them, everything becomes a challenge, right? So it becomes very challenging. And on top of that, So today we don't end up with one system on package, but maybe hundreds of these are connected together. So just like what we had huge supercomputers, so all this are coming to a same board. So individually, earlier we used to have big server rooms with racks with multiple devices connected. So now all of them will become part of connected SOPs, right? So the performance is increasing hugely, but same way the need for verifying these complex devices and the bugs that we can see are also very complex. So if you see here the top flow, so this is how traditionally we used to uh, verify a package, right? Or traditional how a chip and a system looks like. So we have a single chip, we package them, then it is placed on a board, and with device drivers and softwares, we get a full-fledged system. So now there is no more a single chip. So multiple chips are packaged as a system of package, and this complex package has to be on a board, and in the same board there can be multiple SOPs, and finally we need to have a software and the device drivers, and this system becomes much bigger, right? So the major drivers for this complex system is because of the workloads from AI, which has completely revolutionized the way how chips are architected, and that has become the focus from architecture from chip has shifted to how do we architect a complex SOP or a system as a whole, including software. And with the new capabilities or the raw power what we have with today, so silicon is finding its place in multiple areas which were very difficult earlier. Like for example, recently there is a lot of calculations for molecular calculations and in medical field, so which were traditionally not possible are now possible with complex chips. And we always think of not as a chip but as a software defined system, right? Because of the complexity and the use case. So when we had a single chip, building a software was much easier, but when we have a complex chip, building a software for that is really a challenge. So chips have gone into every domain which were not there earlier, and that drives the need for a different types of workload, and each of this are in a different area, so different challenges come. Like for example, with automobile, with autonomous driving, so there is a lot of interfaces with the sensors. Whereas when we do something on the AI, so there's a different type of workload. So for all these scenarios, the system should be stable. So, so as with the device, most of the devices or the chips, we are able to reach a bigger size, and how do we get more PPA? So new technologies like 3D technologies where we stack one device above other, and having different dice
Yeah,
with
Jebin, you've
different.
got 5 minutes left, please, Jebin.
Okay. So, and having dice on different technology. So all these are helping in this cause, right? So as a system of package, the challenges we have is on power delivery. How do we make sure the silicon works properly, right? When we try to connect multiple, and what are the thermal challenges, packaging and board challenges when we have the complex chip, and how do we make sure that we test this at scale. So all these challenges are getting magnified. So today we'll just focus on how uh, from the RTL scope, right from RTL to simulation, how what are the challenges and what are the opportunities we have. So from a methodology perspective, these are the few things which I have listed out. So bringing up a design, right? So typically we used to bring up a single SOC. Now we need to have multiple SOCs integrated together for emulation, for simulation, and even for RTL quality checks, right? For a lint. Uh, so how do we take care of this? And the next one is the resources. We, as the design scales exponentially, we cannot afford to have a huge runtime and memory, which will match this, right? Because if a test case is running 2 hours at an SOC level or 2 days at SOC level, we cannot expect it to run for 20 days when or even 10 days when 10 days if we have 5 days, right? So we cannot expect that. So we need to have methodologies to optimize that. And at the SOP level, at the package level, a lot of new protocols are coming in, right? Like D2D, different die-to-die protocols, and getting a proper knowledge and debugging them is a challenge. So, and also the design, as we see in this diagram, it can be stacked in different ways. There can be horizontal connectivity one over the other. So complex systems, it becomes nightmare to debug at this complexity. So it becomes very important to have a clean and more efficient package level verification. So mainly when we bring up a design for multi-dies, so there are multiple dies and each die can be in a different technology nodes. So when we stitch them together, we need to have methodologies to take care of that, where we don't get conflicts because of the same IP can exist in different dies, and the IP can be of different versions, maybe one generation earlier or a new generation, and these can contribute to different functionality and they can be of different nodes. So we need to handle this complexity as well. And also at the package level, we need to have options to override an IP.
Jebin, just a 2-minute warning, please.
Sure. And also at the package level, we need to have way of overriding an IP or an connectivity for debugging or for any ECOs. So all this capability should be there in the methodology. So same way, what are the real challenges we face in simulation? So when we bring together multiple dies, the traditional simulation will not scale up. So we need to have distributed simulations where the compiled models, elaborated models of each of the dies are controlled by a central system and which will take care of handshake. So this brings more complexity and scheduling and everything becomes a challenge. The same is applicable for static checks also, like lint and CDC. We cannot go with the traditional approach. So we need to have a proper methodology right from the start. So issues which were not expected, like combo loops, where we end up with infinite loop scenarios can creep in. So all of this needs to be taken care. And the last slide, where we mainly focus on the complexity, right? So so traditionally it was IP, sub-IP, subsystem, and dies. But with chiplets, it's collection of dies. So any challenge here, debug and root causing and fixing is time consuming and challenging. And with multiple new protocols and each of these new generations and with increase in bandwidth, having a proper verification IPs and proper design environments is also a challenge. So overall, with all this complexities, still many multi-system on packages are getting produced and they're adding value. So if these important things are taken care, we can make sure the design is of good quality and it's on time. So that's all I have.
Perfect. Yeah, you're just on time, just like your SOP. So and the verification. So thank you very much, Jebin. Perfectly timed presentation.